Mean value theorem. There are two theorems on the AP test that you might state specifically by name. One of them is the intermediate value theorem. We talked about that earlier. Actually, I'll re-talk about it in a minute. And this one, possibly the mean value theorem. Mean, not nasty, value theorem. Don't put not nasty, they won't know what you're talking about. But before we talk about that, we've got to talk about a different theorem. Rolle's theorem. Let f be a function. A couple things has to be true about f. One of the things that must be true about this function is it's got to be continuous. Polynomials are continuous. So if I give you a polynomial, you're just allowed to go, oh, that's a polynomial. It's continuous. It's got to be differentiable. Now notice the difference here between this one and this one. Closed interval, open interval. The closed interval, the continuity, remember we talked about continuity from a direction. You can have continuity at an endpoint as long as you think about the limit as being a one-sided limit. But excuse me. But they don't do that for differentiability. You can't talk about the derivative at an endpoint. So it's by using the open space, the open interval, that means not up to a, but as close as a as you want to. And so whatever value you pick, you're not at the endpoint yet. So get as close to a as you need or as close to b as you want, but you're not at a, you're not at b. There's always another point on the other side, so you can still do a two-sided limit when you're talking about differentiability. And then f of a equals f of b. What in the heck does that all mean? What it means is that, or something like that. It's continuous. I can get from here to there without lifting up my pencil, jumping, whatever. It's differentiable. I can take the derivative at any point in that. And last but not least, f of a equals f of b. In other words, whatever f of a is, it's equal to f of b. Maybe it's 2. Made it up. What could it be? How could 1 and 3 be true but not 2? What would it look like? That's almost like that. What do you think, Logan?
Vertical line from the spot where it starts to the spot where it finishes. So you draw a vertical line anywhere. And A and B are the same point.
But I don't have a B. I'm not on B.
B is the same point as A.
No, it's not. A's over here, B's over there. F of A and F of B are the same point, but this is saying you have all the points from A to B. There is a graph from A at every point from A to B. This doesn't give me a point from every value from A to B. Yeah, so how could this be true and this be true, but not this guy? Like that?
No, like the same graph you have would just extend like down to the end.
But then f of A doesn't equal f of B. No, I don't want this one.
You could have
like a vertical, yes.
just like that.
That's what you did with your finger. I'm not sure what your words were, but that's what you did with your finger. It's not differentiable at this point because you've got that little cusp thing going on, right? The limit from both sides, the slopes are not approaching the same value. One's approaching positive infinity, one's approaching negative infinity. If you were graphing the derivative at this point, at whatever that value is, from this side, it's approaching positive infinity. From the other side, those are all negative slopes, and it approaches negative infinity. That's what the derivative would look like. It's not differentiable at that point. It's undefined. For Rolle's theorem, for what we're about to talk about with Rolle's theorem, all three of those must be true. And if all three of those things are true, than this. Now what's that mean? There's a max or a min. Yep. Essentially, graphically, it means this. If I am here, if I am here, and I end up at the same level over here, the only way that I could get back down to that same level is if somewhere it turns. It's got to turn somewhere and come back down. Or the graph could do this kind of a thing. But somewhere there's going to be a horizontal tangent. Maybe there's more than one. Even if I go straight there, what's the derivative at this point equal to? 0. If I start at 5 and I end at 5, y value 5, somewhere in between, the slope has to be equal to 0. I can't, or if I start at 3, if I'm at 3 and I end at 3, somewhere in between the slope is 0. The instantaneous rate of change is 0. Yes, sir.
Dave.
You have 2 minutes.
I'm looking at that clock.
All right. See you, bye.
Bye.
Now, this is an interesting application of this. This is not like, oh, there are going to be 20 problems like this one. This is one little itty-bitty kind of a concept. Not a huge deal. But it's a use of Rolle's theorem. So this is saying prove there's only one root. Prove only one root. Now, you could graph this thing and look at the picture and go, oh, you have to cross this. Back so soon?
Yeah, I'll make this here.
Okay, thanks. So, like I said, you can graph it. You can see what it looks like. You can say, hey, look, it crosses once. But here comes the mathematical. If we didn't have the calculator, if we weren't just graphing the thing, mathematical proof of this. If there's one root, maybe there's more than one root. So what I'm going to do first is figure out if there is one root. And we're going to use this using the intermediate value theorem. Well, let's remind about what that is. The intermediate value theorem says if at A you're at this level, and then when you get over here to B, you're up at this level, that means you touch every single answer in between f of A and f of B. If the river level on Monday morning is at 10 feet, and then there's lots of rain, and on Tuesday morning it's at 15 feet, was there ever a time when the river level was 11 feet, or 12 feet, or 13, and so on, right? You got to hit every value in between. The river can't go from 10 feet to 15 feet without passing through every single number. That's intermediate value theorem. You may cite that in a proof, in a demonstration, or how do you know this? Well, intermediate value theorem says if this is a continuous function and f of A is less than f of B, then you're going to touch every single value between f of A and f of B. Yes?
If you're going to use the intermediate value theorem, do you have to prove that it's continuous, or can you just say it's continuous? Like
If it's a polynomial, you can just say because it's polynomial, it's continuous and differentiable. Just make that statement. So that cuts out, you satisfy the conditions of that. But you do need to acknowledge the conditions of that. So I'm going to randomly pick two numbers, 0 and 1. Now, it wasn't really random. I kind of had some good guessing going on here because I kind of sort of knew what the graph really looked like. But I randomly, quote, randomly picked 2 points. Well, let's plug in 0. When I plug 0 into there, you come up with an answer of -1. When I plug in 1, 1 plus 1 is 2, minus 1 is 1. Now, talk to me about intermediate value theorem. Why in the heck am I doing that? Keeping in mind I'm trying to prove roots. So, by the intermediate value theorem, this polynomial must touch every single point between -1 and +1. Therefore, there is a value c such that f of c equals 0. There is a root. Because this goes from negative to positive, there's a root somewhere in there. Now, what I haven't proved is whether the graph does this between 0 and 1. All I've said is it goes from negative over here at 0 to positive over here at 1. But the question was, prove that there's one root, only one root. Ever. Not just between 0 and 1. Now, step forward a little bit. Think about what Rolle's theorem said. If this is a root, and this is a root right there. In other words, f of a and f of b are equal to each other. Ooh, glance at your list there real fast. Number 1, it's got to be continuous. Number 2, it's differentiable. This picture I've drawn, the graph's differentiable everywhere. I don't have points, so it's supposed to be curves. And 3, f of b is equal to f of a. If this is what the picture looks like, here's a place where f of a and f of b are the same value. If that's what the picture looks like, what must be true? What's the conclusion? There's got to be a number c where
f prime of c equals 0.
Wow, that was cool the way you threw your voice. Yeah, f prime of c is good. There's got to be a place, if this graph comes back down and crosses again, there's got to be a place where there's a horizontal tangent. Right? I mean, look at the picture. The only way to get back down is to have a horizontal tangent somewhere. That's what Rolle's theorem says. So what I'm going to do is I'm going to assume there is another point. Okay, let's find that other point. Let's figure out where this is. There's got to be another point somewhere that has a 0, or that is a 0, or a root of the polynomial. And if that's true, then Rolle's theorem should be true, right? Because it's a polynomial, it's continuous, it's a polynomial, it's differentiable, and I'm saying, hey, there's probably another point somewhere where there's a root, which means f of a and f of b are both equal to 0. So therefore, by Rolle's theorem, there must be some place where f prime of c equals 0. So let's find c. Let's find that place where that's true. Rolle's theorem says there must be some place where the derivative, where'd it go? There it is. There must be some place where Rolle's theorem, or there must be some place where the derivative is equal to 0, according to Rolle's theorem. We buy that? So let's find it. What do you notice when you take the derivative?
It's just 3x squared plus 1.
3x squared plus 1. And that's got to be equal to 0 somewhere, if Rolle's theorem applies. Notice I didn't say if Rolle's theorem is true. Rolle's theorem is true. The question is, does it apply in this situation? And so when you solve that equation where this thing's equal to 0, look what you get.
Evil no.
You get a big fat no. Now somebody tell me what you think I'm doing here. What's happening in this problem? Maybe just restate the problem. What's going on here? Heidi, what do you got? Okay, so I got one root. I know for sure.
And then you're proving that there's no max or min, so the fact that it never occurs means it can't be a second.
Rolle's theorem says that if it does come back down, there must be a second place. Or, I'm sorry, there must be a horizontal tangent. Since I've discovered that there is no place where the derivative equals 0, then that means this doesn't come back down. It can't look like this. So, does Rolle's theorem apply in this situation? Well, it had to be continuous. It is. It had to be differentiable. It is. The third one says f of a has to equal f of b. So one of those three things must not be true, because Rolle's theorem says this will be true. Well, it's differentiable. It's continuous. So the thing that must not be true is, where'd it go? Is this statement. There can't be a place where f of a equals f of b equals 0. There can't be a place where there's a second root. I know there's one for sure. We found one, right? We found one spot where the answer was equal to 0 by intermediate value theorem. It went from negative to positive, so somewhere in there f of a equals 0. You kind of have to sit on that one a little bit and kind of get your mind around the logic of the problem. This cannot be a true sentence because Rolle's theorem says that if it was, then the derivative would equal 0 somewhere. And since it doesn't, that can't be true. I can't get back down to 0 unless I have some place where the derivative is equal to 0. Yes, sir?
If you do one of those like cusp things where like...
But then it's not differentiable. So it can get back down, but Rolle's theorem, in the equation I've got, it's a continuous differentiable polynomial. So that rules out the cusp. Now, mean value theorem. Mean value theorem is, actually, Rolle's theorem is just a specific example of the mean value theorem. Notice the first two here are exactly the same as the first two of Rolle's. Now I'm going to back up just for a second. These are the first two of intermediate value, or Rolle's rather. If you write down Rolle's, you got them already. Just draw an arrow. Should have to recopy. I'm going to back up for a second. Look at the slope of the line from A to B in this problem. And by the way, it matters not where this stuff is. Well, it doesn't have to be roots. It could be a problem happening up here. Rolle's theorem could apply up here as well, where f of a and f of b are the same answer. But look at the slope of the line between these 2 points. Look at the slope of the line between those 2 points. Look at the slope of the tangent. It's not a coincidence that those two things are equal to each other. This is what mean value theorem is saying. Tuck that in the back of your head, what I just said, because I'm going to pull that up in a second. What is f of b minus f a over b minus a?
y2 minus y1 over x. Slope.
It's the slope. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's just the slope of the line from A to B. This is the slope of the line from A to B. And then this is saying, all right, the slope of the line from A to B, there's got to be a place somewhere on the curve where its instantaneous rate of change is the same as that slope. Can you get a picture of that in your head? I'll come back to this page in a second. This equation is simply the slope of the line from A to B. That's that line. And so the mean value theorem is saying that somewhere on that curve, there's a place where the slope of the tangent line is the same I'm not sure what this little guy is right there, is the same as that equation. There's some place on this curve where the slope of this red line is the same as the slope of the tangent. Do you see that that's exactly what Rolle's theorem was, except it just kind of tilts it? Right? Whatever this slope is, there's somewhere where the slope is the same. Rolle's theorem just had them both going at 0. But it's the same logic. Whatever this slope is, somewhere it's that slope. Somewhere, now listen to this vocabulary. Somewhere on this curve, the instantaneous rate of change has to equal the average rate of change. This is the average rate of change. This is the instantaneous rate of change. Got a story for you. I'll tell you about it in a second. Now let me come back to this equation. The book will take this equation and do some things to it. What they've done is just simply taken the b minus a and multiplied it up here with the f prime. So they got the b minus a multiplying times the f prime. And what's left on the other side is f of b minus f of a. I'm not particularly sure why they do it that way, other than to just get no fractions.
Wow.
But do you recognize this as point slope formula? Y minus the y value equals the slope times x minus the x value. That's all that is. It's the same daggone equation. So, let's do a quick one here. Here's a function on 0 to 2. Find c. Find c such that that's true. In other words, this is just simply the mean value theorem. Find some value c. They word it in the book. They'll say, find a value c that supports the conclusion of the mean value theorem. This is the conclusion of the mean value theorem. So I'm looking for c. At what point on this interval does this thing have the same slope as the average slope? All right, so if I'm going to use mean value theorem, I got to make sure that I've satisfied the conditions of it first. Mean value theorem only has two conditions. The first is it's got to be continuous. Well, this is a polynomial. Polynomials are continuous everywhere. It's got to be differentiable. This is a polynomial. Polynomials are differentiable everywhere. So what that means is there's got to be some number, c, that makes this true. Find that number. Now graphically, and you don't need to graph it, but graphically this is what this looks like. This is the green curve is the curve. And they want the f of b minus f of a over b minus a is the slope of that line from 0 to 2, if this is 2 out here. The slope of that line is f of b minus f of a over b minus a. And this is saying, mean value theorem says that somewhere on this graph, there's a place where the slopes are parallel. Visually, it's easy to see. You could kind of estimate it if you had to. But let me find that value. So I'm going to plug it into this equation, which is the mean value theorem equation, just kind of rearranged, right? So we know what f of b is by plugging. This is b, right? We're going to plug 2 into this equation. You get 8 minus 2 is 6. That's where the 6 comes from. F of a, plug 0 into this equation. You get 0. Equals. Well, here's the derivative evaluated at c. The derivative evaluated at c, f prime of c. And then b minus a, 2 minus 0 is 2. Hey, good news. Lovely little equation, only one variable. Yeehaw. It's all for c. So do a little arithmetic. Divided both sides by 2. Subtract, add 1. Divide by 3. Take a square root. Ooh, what do you notice? Uh-huh. Got a positive and negative. Ooh, but wait, you say.
Oh, but wait.
It's not on the interval.
It's not on the interval, one of them is. So we ignore that second one and only look at the positive side of it. So 2 divided by the square root of 3 as the point at which the slope of the tangent will be equal to the average rate of change. The average rate of change is just that straight line from end to beginning to end.
I love math.
Yes, sir.
Can you go back to the slide before you did the graph? Yeah, one before this. Thank you.
Yeah, Brooke?
Is it ever not going to be on the interval?
No, because you have to have a starting and ending place. Yeah, the f of a, f of b minus f of a. I gotta know where to, because if I change that interval, that's going to change the slope, which changes where on the curve you have the tangent line. All right, so here's my story. Maybe. Anybody know what that's supposed to be? Oh, very good. Yes, Ohio. Nicely done. Many, many, many years ago, I was driving from, I don't know where I was, but I was going to some place over here on the eastern part of the state. I can't remember where I was, somewhere up here. Someplace. My parents used to live in Minneapolis, so there was an outside chance maybe I was seeing them in Minneapolis. Anyway, I was coming across and I had to go to this place over here. And across the northern part of the state is a toll road. It's like Interstate 80, 90, they share together for a little while. But it's a toll road. You get on the toll road, they give you a ticket. Now the ticket has on it stamped when you got on and where you got on, right? And so I was running late. So the moment I got on, what I'm going to graph is S of t here. This is my position function. I got on and I was getting off, I don't know, somewhere down over here, someplace I got off and then cut down. But this is my position function, say, right? So sometimes I went fast, sometimes I got stuck behind a truck and I went slow, so sometimes I would go faster, whatever. Let's, just for sake of purposes, round off. Let's say I drove 90 miles. Actually, it's probably more than that across there, but let's just go with 90 and keep the numbers easy. And I did that in 1 hour. So if I went 90 miles in 1 hour, my average rate of change, of course, is 90 miles an hour. That would be the slope of that line. Sorry, I put the 90 in the wrong place. So rise over run. The slope of that line would be 90. Okay, I confess, I was speeding. I'm not even a Boy Scout. This is Boy Scout, isn't it? Yeah. Oh, Boy Scouts are too?
Boy Scouts or military?
Military. Oh, really? Is that really?
One holds up 2 hands.
Okay, what's one finger? Pick your nose? Okay. Anyway, so I have to confess I was speeding. Now, here's what I'm thinking. As I'm driving along speeding, and I'm thinking, all right, when I get to the end and I get to the toll booth where I'm supposed to pay, I'm going to hand them this ticket. This ticket will say where I got on the toll road and at what time I got on the toll road. And then they're going to be able to look at their watches and say, you had an average rate of change of 90 miles an hour, or a velocity, an average velocity of 90 miles an hour. Now, I could say, well, that doesn't mean I was actually going 90 miles an hour. That was just the average. But I got to thinking, perhaps the person at the toll booth understands the mean value theorem. Because what that says is, if I have a slope that it has an average slope of 90 miles an hour, somewhere on this graph, there is a point where my instantaneous rate of change is 90. So using the mean value theorem in a court of law, they could actually prove I was going 90 miles an hour, if only for an instant, even though they weren't there. Because they would know my average rate of change. So what I did, I told them I lost the ticket. Oh, it blew out the window. Now, when you do that on a toll road, you end up paying the whole toll. You know, they make the assumption then you're on the road for the entire time, for the whole distance, and so you have to pay the highest price that the toll is. Now, I had gone almost the whole way anyway, so it was only going to be a couple extra bucks, but I thought, this is a good way to avoid a ticket. It's worth the extra couple of bucks just to make sure I don't get a ticket. Because they were going to be able to tell that I was clearly had been speeding. So to avoid the possibility of the ticket, using the mean value theorem, they could prove my instantaneous rate of change was in fact 90 at least once on that trip. At other points, it was more than 90. But they could prove it was 90 at least once, if that's the average rate of change. Now maybe I only went more than 90 for a couple of seconds. You know, like maybe I went like 400 miles an hour just for a couple of seconds.
Add the rocket.
Right. Kick the rocket, the booster pack in. So
illegal 69.
So as it turns out, I was out a couple of bucks, but I got to thinking, I don't see why not. Now, as I thought about it in later years, I realized I could have said, well, I gave somebody a ride, and they were driving for a while I took a nap, and then I dropped them off at a rest area. Bus stop. Well, no.
Do they give tickets for that?
I don't know, but I wasn't going to take the chance. Because the tickets are going to be like, $100 or more, and I didn't want to pay a big old fine. Don't speed. Wear your seatbelts. Don't text while driving.
If you do speed, keep in mind that calculus can help you.
But literally, that's the logic of the mean value theorem. That push come to shove, given a smart prosecutor, they could have said, if your average rate of change is 90, guaranteed for sure, you had an instantaneous rate of change of 90 somewhere during the journey. And so even though they don't have the radar gun on me at that moment, they can prove that I was going 90 miles an hour. Once. Therefore, speeding, therefore, here's your ticket.
Try explaining that to Jerry.
Yeah. Good luck.
Can I do this?
All right. Next one. Another example. I'm going to do this the simple way, then I'm going to do the calculus way. Sometimes the calculus way is the simple way, not in this case. So what this is saying is f of 0 is -3. So here I am down at -3. And they tell me something about the slope, right? It's a derivative. And I'm saying the slope is less than or equal to 5, which means at most it's 5. It's never more than 5. But it could be equal to 5. How big can f of 2 be? Well, let's assume for a moment that my slope is equal to 5 every single step of the way. So if I start at 0, -3 down here, and I do a slope of 5, I go up 1, 2, 3, 4, 5, and over 1. Do it again. Now I'm at 1, right? I'm at f of 1. And then go up 5 again. Darn. There it is. 1, 2, 3, 4, 5, and over 1. So now when I'm at f of 2, that's the value where I am. I've gotten up to 7. So what's the largest f of 2 could be? 7. Now, that's easy with small numbers. Let me do it with a little larger set of numbers. Or not do it with a little larger, but to show you a way you could do if you had a larger set of numbers. I'm going to come back to this theorem. Right? That's the mean value theorem, just kind of rearranged. So, in this problem, they told me my starting point, A was 0. They told me my ending point, 2. They told me what the starting value was, f of A. And what is it they're looking for? Kind of almost what's left. Question was, how high up can this be? What am I looking for? F of B. So the missing piece of information is what's f of B. They even told me what f prime was. They told me the slope was 5. Hey, thanks. so I'm going to plug everything into this equation. So here's f of b. Here's f of, here's f of b, right? I don't know what f of b is. It's f of 2. Here's f of a, the starting point, -3. I'm going to assume that the slope is 5 everywhere. And then b minus a. And so the largest value you could get for f of 2, solve the equation, is 7. In other words, what if the instantaneous rate of change was exactly equal to the average rate of change the whole time? In other words, what if I drove 90 miles an hour the whole time? I pulled out, I went through the first gate, I grabbed the ticket off the thing going 90 miles an hour, right? And threw coins at them as I went through on the other side. That's what this assumption is. So the assumption is here, you're doing a slope of 5 everywhere. Well, you probably don't, which means the answer is going to be a little less than 7. As long as it's never more than 5, the slope's never more than 5, I can't get an answer more than 7. That's it. That's the way this works. Mean value theorem. The instantaneous rate of change at some point must be equal to the average rate of change. Average rate of change is simply the slope of a line. No calculus involved. Average rate of change is just the slope of the line from the beginning to the end. No calculus. But somewhere in that journey, the mean value theorem says the instantaneous rate of change must equal that average rate of change. At some point in time, I had to be going 90 miles an hour since that was my average speed. The end.